Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Pleased to introduce to both of you Michael Armbrust, who's a very exciting grad student at Berkeley. You finished 5 years now?
I will be finishing in December, but
and he will be finishing in December, and he's doing a, if I remember correctly, you're doing a postdoc down there for 2 years, year and a half.
Yeah, 2 years. 2 years.
Yeah. And then we'll be on the market looking for a real job, and we would love to have him come up here and interview when he wants a real job. But in the interim, I've invited him to come and talk about some of the work that he did with the Brad Lab versus AMP Lab, or it kind of crossed.
Yeah, both of them.
You know, the project name changes every 5 years, but the components change in different offsets. So he's going to tell us about PIQL, which I personally really think is a great idea.
Okay, thank you very much, Bill. So I'm here to tell you about PIQL, which stands for the Performance Insightful Query Language. And basically, the idea is we're going to let you build web applications that scale to arbitrary sizes while still guaranteeing response time. So kind of the model, the world that we're living in is these kind of interactive web applications. Think things like Twitter, Bing, Facebook, et cetera. And kind of the thing about these applications is they grow very rapidly. So this graph here is the number of tweets per day since Twitter started. And as you can see, it was growing exponentially and continues to grow exponentially over time. And so in order to keep up with this demand, it's very difficult for these systems to scale. Kind of what you typically find is when you get overloaded with all of these users because your application becomes popular, you often end up with what we call a success disaster, where because you became so popular, your application servers and your databases tip over, and you actually start scaring users away because your application can't keep up. So when you look at what the problem is when these sort of success disasters occur, it's usually the database that is the problem. So it's actually, thanks to cloud computing, pretty easy to add stateless application servers. So you can kind of scale those up arbitrarily as demand increases. But it's actually much harder to scale these stateful storage systems where kind of all of the difficult logic is and concurrency issues occur. And so, you know, Twitter actually did an analysis of all of the problems they were having a couple of years ago, and they found that most of it was because of these bad queries that were being generated by Active Record, causing really slow things to occur in the database, which was then knocking other queries out and causing the entire system to slow down. So kind of, there's a couple of reasons for this, why traditional relational databases are kind of hard to scale. And one of them is data independence. So, you know, data independence, for those of you who aren't familiar, is kind of the idea that you write these declarative queries which specify what data to retrieve and not necessarily how to retrieve it. The nice thing about this is it allows optimization and independence from the physical and logical schema. So you can add columns, remove columns, add indexes, and you don't have to change anything in your application. Additionally, the optimizer is free to kind of go and decide what the best plan is. You as the application developer don't have to worry about that. Kind of the con here is these performance problems are often hidden until they cause issues in production. So you're running over a small test data set at small scale, and you don't realize that this could be doing an entire table scan. So kind of the dirty secret of traditional relational databases is that these declarative languages kind of hide the underlying complexity of the system from the developer. Another issue is the way that this optimization occurs. When it's deciding amongst all of the different plans which one it should actually use, the way it does this is by looking at the minimum average cost based on statistics. So kind of to give you an example of where this has actually caused problems in production at Twitter, let's take, for example, the query that creates this line of the web page. So when you go to the AMP Lab's web page, it shows you which of the people you're following are also following the AMP Lab. So there's kind of two different plans that the database can choose in order to execute this. It can do a sequential scan over a single level index, or it can do a bunch of random reads against a second level index. And so the way the optimizer is going to decide which of these plans to use is going to look at statistics. And it's going to say, you know, how many followers does the average person have? So the AMP Lab only has 150. The actual average is 126. So on this graph, it would look here, and it would say, well, clearly the unbounded index scan plan is much faster. And so that's what the optimizer would suggest. However, then when you have an outlier like Lady Gaga, who has 19 million followers, that the performance is going to go through the roof, and you're going to have 10-minute latencies to answer this question. And so kind of the dirty secret here is that this minimum cost optimization fails for the 0.1%. And you do need to care about those when you want to keep these high quantile SLOs. I'm glad you got that. So kind of the recent trend for these developers of these large-scale web applications has been to switch to these NoSQL solutions. So these are things like Bigtable, Cassandra, or MongoDB. They provide you just simple key value lookup. Sometimes they also allow range scans. And the reason developers really like these systems is because it's very easy to reason about the performance of these simple operations. Anytime things get slow, you just throw more machines at it, it partitions the data further, gets and puts return in basically constant time, independent of the size of the total database. The con here is that this is really throwing the baby out with the bathwater. You're losing all of the benefits of relational databases and declarative languages in order to get this kind of performance. And so by only giving developers these simple operations, you're forcing them to reinvent a lot of complex abstractions that a lot of really smart engineers have thought about for many, many years. So they have to kind of do the optimization by hand, they have to maintain indexes by hand, and then when things change underneath, you end up rewriting your programs instead of letting the optimizer do it for you. So instead, we propose PIQL, the Performance Insightful Query Language. And the idea is what we want to do is we want to guarantee scalability even for sophisticated relational queries. We're going to do this through a number of techniques. First of all, we're going to build on top of these existing scalable key value stores that we can leverage all of the engineering work that has gone into them. We're going to, however, give you an interface that is slightly higher than this get and put. We're going to give you a full relational query language so that you can retain those productivity benefits. The optimizer is going to ensure that all of the queries of your application, kind of statically at compile time, are scalable even for outliers, and make sure that you're not going to have any kinds of scalability problems. And in order to do this, it's automatically going to create any indexes or materialized views that are needed, but only if they can be proven scalable. And I'll talk more about the techniques we use in order to do that. And then finally, I'm going to show you how we actually have a model that allows you to take the number of operations that are performed by any given query and use that to reason about the SLO compliance of the overall query. So kind of the general workflow when you're using PIQL is like this. So a developer writes an application in their favorite framework. It can be Scala, it can be Ruby on Rails, it could be .NET. The system actually pulls out all of the queries from it, and the PIQL optimizer either says, yes, oh, you have some problems. You need to fix these queries. These are not going to be scalable. Or it produces scale-independent query plans. I'll talk a little bit more about what that means in upcoming slides. A list of views and indexes that are required to actually execute these queries efficiently, and then predictions for the SLO compliance of all these queries so you can see if it's actually going to be fast enough to meet the needs of your application. So kind of the architecture of the system, as I said, we build on top of these existing key value stores. PIQL is written as a library that you can link in with your application. Basically, you write in the queries, and then it decomposes those queries into key value store operations. We have a couple of requirements of the underlying store. Basically, we expect it to have things like get and get range, where we can kind of do efficient lookups either by the whole key or by a prefix of the key. We assume that it's going to give us scalability with predictable performance. So we assume that it's taking care of kind of reprovisioning as load increases, or as data sizes increase. And there's a lot of other work that I'm not going to talk about today that was done in the lab on ensuring that that's possible. And then finally, we're not going to worry about consistency. We're basically going to give you whatever consistency model the key value store has. So there's a lot of work on kind of getting better consistency guarantees out of key value stores, but really whatever this key value store is giving you, the PIQL library is just going to give to the next layer up. So kind of the rest of the talk is going to be split into a couple of parts. But basically, the key idea is I'm going to define different classes of SQL queries where we can guarantee them scale independent based on the resources that they're going to require for their execution. So we're going to start off by talking about the queries that can be executed on demand, so where we can actually calculate the answer when the user asks for it. And in order to do this, I'm going to show you how you can take a relational query and map it to a bounded number of key value store operations. I'm going to talk about how you need to change SQL in order to make the static analysis possible for complex queries and kind of the extensions that are required. And then finally, I'm going to talk about our model for predicting SLO compliance. Since this isn't sufficient for all of the queries you're going to find in these large-scale applications, I'm also going to talk about how you can leverage scale-independent precomputation to increase the space of queries that can be answered by shifting some of the computational work from query time to insertion time. So I'm going to show kind of an algorithm for transforming a scale-dependent query into a scale-independent one that runs against a precomputed answer. I'm going to talk about how we can do a static analysis of that precomputation to ensure that both the storage and the maintenance costs are also bounded, so that those themselves don't become scalability bottlenecks. And I'm going to talk about kind of how you can extend this even further to leverage parallel execution and data aging. And then finally, I'm going to conclude with some ideas about future work, but I'd love to hear your ideas on what's missing or what else could be added to this. So let's start off with scale-independent optimization. So the idea here is we want to be able to bound the work a priori for all of the queries in a given application. So kind of to formalize this a little bit, say we have all of the queries in application Q. So we've done some static analysis, and we've come up with this set Q of all of the queries in an application. Basically, the PIQL optimizer is going to ensure that it can come up with this constant, C sub ops, for every query in the system, such that even in the worst case, the number of key value store operations to execute it will be less than that constant.
Can you specify the constant in your PIQL query?
So basically, it's specified based on the cardinality constraints. The constant for any query is specified by the cardinality constraints that you've specified. What you can specify is the SLO that you want. We can tell you if that number of operations can be performed within that SLO or not.
That's good. Yeah. Really, when I'm writing this, what I want to be able to say is I'm going to get an answer back in X milliseconds.
Exactly. So yes, so that is what the developer tells us is what their is.
That's even better than X operations.
Yeah.
I can explain them to management then.
Yeah, exactly. So how do you actually do this for a relational query? Let's start with kind of a simple example. So I have a SQL query here that basically looks up all of the posts in a given application. So this is something like Twitter or some kind of pub subsystem. I want to look up all of the posts by topic, ordered by the timestamp, and then I want to take the top 10. So kind of what the database is going to do is going to take this SQL query. It's going to map it to a logical plan that says, take all of the posts, filter out all of the ones where the topic ID doesn't match the topic, and I'll point out that this is actually a parameter. So while you have to specify all of your queries ahead of time, you can parameterize them and then kind of fill in those parameters at runtime. What the optimizer does then is it kind of analyzes the query for all possible values of that parameter. So it's going to filter them by the topic ID specified at runtime, sort them, and then only return the top 10. So this is a stop operator, which basically just returns the top 10 tuples that come to it and then ends the query. So these logical operators can actually be mapped to a single getRange call against the key value store, assuming you have an index that's ordered by first topic ID and then timestamp. So one key value store operation can answer this query given this index. To kind of generalize this, basically we have this model for what an index scan can handle. So it's any...
It's one operation, but the amount of stuff that it returns might be unbounded.
But the stop... OK, so as you can see here,
The
stop is required. Yep. Yeah. So that is why the stop is not dotted. So the index scan is some relation with some predicate, some optional number of other predicates, an optional sort, and then yes, the limit is not optional. That is required in order to be scale independent. Exactly. So in general, anytime you see this set of logical operators, it can be mapped to a single getRange call. No, so the sort is actually also put into the key, right? So we're assuming that our key value store is range partitioned. And so kind of in the case of this example here, the index would be over topic ID and then timestamp. So when you look up the topic ID, then all of the rows will be sorted by timestamp next. So you don't need to retrieve them all.
Ordered by some kind of a function, ordered by timestamp plus whatever any kind of function. Then there's not as much.
Well, okay. So if you're right, yeah, okay. That good question. So of course the expression that you're sorting by needs to be calculated using only the information in that single tuple and cannot be based on any joins. Or the data that you're going to be sorting needs to be already bounded due to some other constraints in the query. That is correct. Okay, so index scans, and then if we want to generalize this, we can also support kind of joins as well. So in this case, we're looking at a foreign key join. This is where the attributes in the bounded child plan, so we have some number of tuples coming in, and we know that they're bounded due to kind of the PIQL guarantees. They contain the primary key of another relation. That's what these predicates are representing. And because for any given primary key, there can only be one tuple, we know that we can answer this query by doing, at worst, the number of entries in the child plan gets against the key value store. To generalize this further, we can also handle joins that don't necessarily involve the primary key as long as there's a stop operator at the top. So in this case, we have a bounded child plan, some number of predicates, a sort using the same conditions as we talked about before, and then a stop operator up at the top.
Even with an assumption, your implicit assumption that thing is a brute with a line are already ordered. So that's why your stock condition can really stop.
Absolutely. Absolutely, yes.
That's kind of maybe some kind of restriction here.
Oh, yeah, I mean, this is not full SQL. This is the subset of SQL that can be guaranteed scale independent. And I think the claim that we're going to try to make is that this is sufficiently general to build all of the web applications that exist today. Because basically, if you're violating these, you're probably doing something that's difficult to scale and therefore Facebook couldn't be doing.
So you may not have sufficiently elucidated your important top-level point, which is he's created a query language that if you write in it, then your applications will have well-known scaling properties. So the idea is you develop your applications to this restricted set of things, and you accept the limitations that come with it in exchange for not falling over when you have a success disaster. Right? That's the whole premise of this. It's not as general as SQL, but it's much more scalable. Right?
Yes, I think that's a good summary. So we can also handle joins, which is something that, a lot of these other kind of, you look at the Google query language that they have on App Engine, or you look at the Cassandra query language, this is kind of a level up. And I'll talk about exactly why we're able to do that for a large number of queries. And really what it comes down to is, if you look at some of these harder queries, just standard SQL isn't enough to specify all of the information that the optimizer needs. So here we have kind of a standard timeline query. This is, think once again of a pub subsystem where we have some number of posts and people can subscribe to different topics. This is showing for the current user all of the posts for all of the things that they're subscribed to, ordered by time, and then show me a page of that. So right now, PIQL would reject this because this isn't bounded and this isn't bounded either. So the question is, how can we give this extra information to the optimizer that will allow it to understand why Twitter is actually able to do this safely? So we're going to extend the language in two ways. First of all, we're going to make it easier to bound the amount of data returned. So SQL has a limit operator, which you can also use with an offset. But using that is actually n-squared work to go to each next offset. So what we've done is we've built pagination, the ability to look at the results of an unbounded query one page at a time, as a native operator into the engine. So kind of what this is doing when you tell a query that it's going to be paginated, is you can turn this unbounded query into an unbounded set of queries themselves that are bounded. So each interaction with the database now has a bound. So by adding a paginate to that query, we actually insert this pagination stop operator up at the top. There's still a problem with this query in that the intermediate results of this join could be unbounded. And the way we kind of let the developer tell the database that that's OK is by letting them specify cardinality constraints on kind of the natural limitations due to the relationships that we're modeling. So for example, on Facebook, you're only allowed to have 5,000 friends, which is kind of reasonable since I don't think anybody really interacts with more than 5,000 people in any meaningful way during their lifetime. Unlike SQL, we actually let you express this as part of the DDL of your application. What the database does then is when you filter on any of these attributes that are constrained, it can actually insert a new type of stop operator called a data stop deeper into the plan. The reason we're able to push this stop operator much deeper into the plan than you can with standard stop operators is because they're actually promises about the data, not things that we're enforcing at query time. These cardinality limits can be enforced at insertion time, so we know that there is no more data than that in the database. So they can actually be pushed past predicates that might be reductive. So kind of now that we've made these two extensions to the SQL language, it's possible to take this query, this can be turned into an index scan, and this can be turned into a sorted index join, and now the entire query is bounded. So now that we've got a bound, kind of going back to Bill's question, is any bound acceptable? If I do 1 billion key value store operations, is that OK? And of course it's not. So what we've done is we've actually built up a model that allows the PIQL to both suggest solutions to scale-dependent queries when it can't come up with a bound. And then when it does have a bound, it actually will suggest what cardinalities are acceptable. The way we do this is by taking empirical measurements of single operator performance against a real key value store running on your real hardware. So kind of in this example, what we've done is we've measured an index scan of cardinality 100 with records on average 40 bytes long, and we've created a histogram of the response time. The nice thing about this is since it's a real measurement, it takes into account things like garbage collection or network blips or other things that are going to cause the long tail and affect your 99th percentile. So since we know for each operator the worst case cardinalities, we can actually then look up in all of our empirical measurements for any given query, look up the empirical measurements for each operator, convolve those distributions, and come up with the distribution for the overall query. From that distribution, we can then calculate the 99th percentile response time. So kind of a question now is, does this work? Is this expressive enough? Do our predictions work? Does this actually scale? So we kind of did an evaluation of this on 2 different workloads. We used TPC-W, which is a standard database benchmark simulating something like Amazon.com. And we also used Scatter, which is kind of our own homegrown clone of Twitter. We started by doing a qualitative analysis where we wrote all the queries for the application and introduced cardinality constraints where the PIQL optimizer suggested them. They all kind of made sense. We did things like limiting the number of topics that any given person could follow, or limiting the number of books that a given author could write. PIQL automatically created all of the indexes needed to answer these queries. And kind of what was really cool is the prediction model was able to accurately predict the 99th percentile response time within tens of milliseconds for all of these queries in both of these applications. We also wanted to do kind of a scale analysis of this. And so kind of the methodology here was we ran each benchmark on EC2 on top of our own key value store SCADs. We increased both the data size and the system size. You can think of this as weak scaling for each point. And we measured both the throughput and the 99th percentile response time at each data point. And so kind of unsurprisingly, due to the constraints that the optimizer was enforcing and the way we changed the objective function for optimization, we were able to maintain nearly perfectly linear scalability as we added nodes and data to the system, and nearly perfect response time even in the 99th percentile. So what we've done here is we've actually defined 2 classes of scale-independent queries that can be executed on demand. So SI0 is kind of the highest level of scale independence. These are queries that we can answer on demand using only the primary index. For some queries, however, the cost to do that will still be dependent. It's going to require a table scan or something. So we'll put these into the class SI1, where these are queries where we can answer them on demand, but we need to create a secondary index in order to do that. So this is kind of the space of all queries that we run whenever the user asks them. But what about queries where we need to use precomputation? So precomputable queries, examples that would not fit into this previous model, are things like we want to do a count. So here, Sergey has like 1 billion followers or something, a million followers. Too many to count on demand. And you wouldn't want to put a cardinality constraint on this because you want popular people to be able to have a lot of followers. Another example is things that are shared a lot. Or kind of a more subtle example is a query that returns the top 10 tweets that are tagged with 2 different tags. So basically what we're going to do is we're going to expand the PIQL optimizer such that it has another choice now when it finds a scale-dependent query. So a query comes in. If it's scale-independent, we do the same thing, and we just produce a physical query plan. If it's scale-dependent, we're instead going to try to select a materialized view that could be used to answer the query for all sets of parameters. We're going to look at that materialized view and make sure that the storage required for it is going to be bounded, independent of the size of the data. And we're also going to make sure that the update costs are also bounded. So I'm going to talk kind of about each of these parts in the upcoming slides. Yeah? Say that again.
I have a query. How do I decide that I should precompute it or just consider that
Well, so if there is no physical plan, if the optimizer is unable to find a physical plan that can answer it on demand in a scale-independent way. So let's look at this example.
Yeah, I understand this. If there's no previous plan, you just do it as scale-independent. But you are the one who decides whether to maintain a pre-computed plan or not. Like for Lady Gaga, for example, okay, 20 million followers, you decide. So I'm going to pre-compute something here. You have sometimes to short something forever as more than
So let me be clear. Is what we're doing is we're not pre-computing it for specific values of the parameters. We're computing it for all possible values of the parameters based on the data in the database. So it's not really we're pre-computing it for Lady Gaga. It's that we're pre-computing it for this toTag query. So let me walk through how we do that, and if it's not clear, stop me again. So this is the toTag query. This returns the top 10 documents ordered by time that are tagged with 2 tags. And as an example of why there is no scale-independent plan using only secondary indexes, let's look at the index that the optimizer would create in order to try and answer this. It basically maps tags to document IDs. And as we were kind of talking about, in this example, you would have to scan past an arbitrary number of ladies before you found one that actually matched up with Tramp instead of the pop singer. So there's no way to do this without scanning through an arbitrary number of tuples to find the 5 or 10 that they've asked for that actually match. However, if instead of computing it this way, we transform this query to actually be a materialized view that precomputes all 2 tag combinations, we can then just do a simple lookup into this. So basically, what this is looking for is it's all 2 tag combinations ordered by time, where we kind of join this tags table with itself. And so what you can see here is now we have this, which is it's stored in an efficient index structure, such that we can jump directly to Lady and the Tramp, then ordered by time, and then get the document ID. So what PIQL is going to do is it's going to automatically create this view for you, and you can use this to look up the answer for any values of the parameters. So how do we actually do this? I'm not going to go into all of the details, but it's in the paper. Please, it's in submission, but I'm happy to pass around drafts if people are interested. But just a high-level overview of how this algorithm works. Basically, we take the query, we remove any predicates that are compared with parameters, and move them up into the projection of the view, such that that's going to define the spatial locality of the tuples that actually exist in the materialized view. We include any attributes that are going to be used in ordering in the projection as well. And then we do a check to make sure that the resulting tuples that are going to be the answer to this query are adjacent in the view. That's because we want to be able to look up the answer by doing a single contiguous get range against the key value store. If they're not adjacent, there could be an arbitrary number of tuples in the middle that you'd have to scan past, and this would not be scale independent then. And then finally, based on past techniques that were invented back in the 90s, we add keys so that we can incrementally maintain this view efficiently. So once we have this view, we now need to make sure that it's going to be safe, that it's not going to threaten the scalability of the system. And we'll start by talking about how we bound the storage of the view. So PIQL, basically the goal here is to ensure that the view is going to grow linearly with the size of the base relations. So the invariant that we're going to hold here is that for all views that are created in the system, there will exist some constant C and some relation R, such that the size of the relation times this constant is bigger than the size of the view in the worst case. So we're going to bound the size of the view as some linearly proportional to the size of this single relation. So how do you actually do that for an arbitrary view? The answer is we're going to use an analysis of expanded functional dependencies. So for those of you who aren't database people, basically a functional dependency is some promise that knowing some attributes will let you know the values of some other attributes. Kind of the easiest to understand example is think of your social security number. If I know your social security number, I know your first name. And there is only one first name for that social security number. So you can think of that as the primary key constraint. With PIQL and views, we actually expand this to include two other types of functional dependencies. We have cardinality constraints that we talked about before. This is just like a primary key constraint, except instead of having an edge of weight 1, we have an edge of weight the cardinality. And we also have equality predicate. Since we're not looking at just the data, we're looking at the data that's going to exist in the join. We add bidirectional edges for any equality predicates. So to go back to our example to understand how this works, for the two-tag view, you would construct this graph of functional dependencies. You then start with the primary key of one relation, which is basically the size of that relation. And then you try to include edges until you either covered all of the attributes that exist in the view, or until you can't, and then you decide that it's not scale independent. So in this case, starting with one of the tag tables, we can cover all of the other attributes and decide that the size is going to be, at worst, k times the size of the tags table. If we didn't have a cardinality constraint on the number of tags per document, these lines would not exist, and therefore there would be no covering of this graph. And basically what that's telling you, to kind of understand how that can cause a problem, think of the degenerate case where you have a single document and an arbitrary number of tags. It's going to be the size of the tags table squared, is basically what this analysis is telling you. So now that we've decided that the storage is going to be bounded, we need to make sure that we can actually incrementally maintain this view as well. So kind of this is going to look similar to the work that we did in the first part of this talk. But what we're going to do is we're going to make sure that for all of the relations in the system, the amount of work required to update all of the indexes and views, given a single update to that relation, there is some constant C sub ops such that in the worst case, that number of operations is less than the constant. So we're going to come up with an upper bound on the amount of work to do all of the maintenance of all of the indexes and all of the views. That is true, but when we expand into the further levels of scale independence, we're going to let you get rid of one without the other, which is why we define them separately. Yeah. Good question, though. You're jumping ahead. So kind of the idea here is the way we maintain these views is using standard techniques on delta queries. So basically, given this view definition, we construct this delta query where basically you take the relation that is being updated and substitute in the tuple that is being either inserted or deleted. And what this query is going to do is it's going to give you all of the tuples that need to be either added or removed from the view. And because of the way that we constructed the view, we know that this is always going to be safe and maintain the view correctly. Since this is now just a PIQL query, we can actually pass this back into the work from the first part of this talk, and it'll tell us if there is a scale-independent plan for doing this. What you're going to notice, though, is that this can actually be invoked recursively. So the maintenance of a view might create another view, but because of some work that was done by some guys at EPFL, we know that that recursion will always terminate. So what this lets us do is define a third level of scale independence, a third class, which we call SI2, where the work to execute the query on demand, even using secondary indexes, is potentially dependent on the scale, but the work to incrementally update and store a materialized view are independent of the size of the data. So now the question is, are we still meeting our SLOs? Since all of this is about meeting SLOs and not bounding operations, let's look again at the two tags query. When you take the two tags query, this is the response time of running it on a real cluster on EC2 from 0 to 200 machines. And what you see is that while the writes remain the time for writes remain relatively constant, the response time for reading blows up as the data goes up, kind of because of exactly what we were talking about. You have to scan an arbitrary number of tuples before you find the 5 that match. The tag data here was distributed Zipfian, and this is a log scale. So this is really blowing up in terms of response time. So what you're going to see is that when we add in the materialized view, we can actually cut down the read time significantly, and not only cut it down, but this is basically constant. You can see it basically stagnates at 8 milliseconds here. And kind of more importantly, we're also able to bound the write time as well. So we're able to cut the response time for reading down significantly with only a mild increase to the write time. And most importantly, the increase in write latency is constant. So there's a couple of ways that we can expand this. One example is sometimes when you look at the delta query itself is not bounded, but can be split up and run in parallel. So kind of an example here is, so if you have, when Lady Gaga tweets, for instance, she has many, many followers, and you want to distribute them to all of her followers, you could have one computer do that serially, or you could have all of the computers that are storing the subscriptions table update their section of the subscriptions table. The idea here is instead of bounding the total size of the update function, we're going to bound the amount of work that needs to be done serially by a single computer. And then all of those will be done in parallel. So effectively, you're bounding the latency before this update is visible to all of the users in the system. So kind of the requirement here is that it's unbounded over only a single relation, because if it's unbounded over multiple relations, you could require arbitrary amounts of parallelism and thus not be bounded. And kind of the cost here is that we now no longer have an upper bound on the total amount of work required by the system. So you might have spiky computational requirements. Another example of how we can kind of leverage this split updates is when you have a page that's paginated by time. What we can guarantee is that the first page is updated in a bounded amount of time and then lazily update the later pages. And so for something like Facebook or Twitter, where 99% of the time users are only looking at the first page, that's acceptable. But due to these costs, due to the way this changes both the behavior of the application or the computational requirements of the application, we require explicit authorization from the developer before invoking either of these techniques. So what this does, it lets us define a fourth class of scale independence where the update cost is unbounded, but the storage is independent of the system. We call this SI3. And of course, there's going to be a fourth. So what do you do with data that grows over time? So the fourth extension that we've made to our model is we allow developers to specify data retention policies for data that grows over time. And the idea here is that many applications often use this more recent data or more often or exclusively. And so the retention policies allow the system to automatically either age data to cheaper storage, where we're not going to give you response time guarantees anymore, but at least it's accessible, or just throw out all data. Don't materialize that stuff. Keep it only in the base relations, and you kind of have to query it through other mechanisms. So the developer must specify the policy and the ordering here, but when it's there, the optimizer will automatically take advantage of it. And this allows us to specify the fourth class, where the cost of storing, updating, or executing it is all dependent, But if you allow us to split and parallelize the updates or and age out old data, then it's going to be independent. So basically, these are the 5 classes of scale-independent queries that the PIQL executor can recognize. And based on them, you can reason about the resource requirements of your application, even as you hit what could be a success disaster. So that's kind of my thesis, basically. Now let's talk about some kind of things that I'm looking at working on in the future. So one issue is contention. Right now, PIQL doesn't really model contention at all, and so it's possible to create something where there's inherent contention in your data model. So for example, if you have some counter that the system is updating and you have every user is trying to update it, PIQL's not going to save you there. Another kind of more subtle example is some kind of hotspot in your index due to temporal locality. So if you try to construct an index of all of the tweets ordered by time, the server that's holding the current time is just going to get completely bombarded. So kind of the challenges, I think, here are, first of all, can you come up with a model that express like insertion locality so that you can kind of understand where contention might occur? And then can you detect these problematic data structures automatically and suggest to the users changes to their data model to fix them? And then finally, can you do something really clever, and when you see this happening, say, well, you probably don't really ever want to see all of the tweets ordered by time, since it's going to scroll by so quickly, it'll be changing too fast for the user to even notice, but maybe you just want a sample of the tweets from the last minute. So can the system automatically leverage approximation or sampling in these cases where contention could become a problem? Another example is expanding the operator space. So right now we only do get, put, get range, but key value stores are getting smarter than that. There are things like coprocessors. Some kind of distributed storage systems are actually things that are much more expressive, like SQL. So I'm not sure exactly what Azure looks like, but I imagine that there's some sort of sharded SQL system somewhere. And okay, and so now the question is, what operators exist in these richer systems, and can we come up with scale-independent operators there, where we can kind of expand these techniques and allow greater numbers of queries to be executed? So I think defining those operators is a challenge. As well as you add more machines, will our SLO compliance modeling continue to work even in the face of stragglers? So since in our current model we're only ever touching a bounded number of machines, there's going to be a bounded chance of straggling, and therefore it kind of worked with our modeling. But if you're going to touch more and more machines as the data grows, are you still going to be able to do this? I think that's an open question. Another example is handling partial failures. This is actually something I'm working on right now and would love to talk about more. But most work on doing incremental view maintenance assumes strong consistency. And so that's a big problem if you have even a distributed system, and especially if you're going to have multiple data centers. You just can't take locks on things for a long time. Otherwise, update processing could get delayed arbitrarily. Just because one server is down does not mean you should not deliver Lady Gaga's tweets to all of her other users, for example. So I think the question here is, what does eventually consistent view maintenance look like? Is there some way to process an update partially, maybe even inconsistently during a failure, do some sort of best effort processing, and then do bookkeeping so that you can realize that there was either a conflict or you were missing some data, and repair these inconsistencies after the failure is resolved? So I think there's a ton of challenges here. I think this area is pretty unexplored. What types of queries is possible? What types of bookkeeping do you need? Is like optimistic concurrency enough and you just check read sets later? So I would love to talk more about this.
So would be any difference between additional consistency for a table and additional consistency for a view?
Yeah, so I think there is, and it comes down to specifically the update processing itself. You want to make sure that it's never possible for a write to just get lost completely.
Yeah, so that's the additional consistency for a table. That's whatever's done now.
So I would say the semantics are the same, but I don't think the mechanisms you use for eventual consistency of a table will work for a view. Because the delta queries that are getting executed are a little bit more complex than doing a single insert or update, right? With like the single insert, you just make sure a quorum gets it, you use Paxos or something like that. That doesn't really work for executing arbitrary SQL queries to calculate deltas. So yeah, I do not know the answer to this one yet, but this is actually the project that we're kind of actively working on and hoping to have a SIGMOD submission for. And finally, I kind of enjoyed playing around with language integration. So as you guys probably know, developers prefer kind of nice language bindings to these opaque SQL strings that the compiler knows nothing about. So currently, PIQL kind of copies a lot of the stuff that LINQ does and is implemented as a DSL inside of Scala. So you specify your DDL as just defining these classes, And you specify your DML as kind of these chained expressions where you represent the SQL operators. And right now we have a prototype of this, but there's a bunch of stuff missing. We don't have type safety for the queries and their results, and we don't have anything with UDF. So I think another nice thing about using a functional language like Scala is you can specify these closures, and it'd be really cool if these closures could actually represent nice language-integrated UDFs. And then the question is, what UDFs are scale independent? And I think there's a lot of work to be done there as well. OK, so that's actually all that I have. Kind of in conclusion, we've defined these 5 classes of scale-independent queries that work against the standard relational model. This makes it significantly easier for developers to build applications that are going to scale trivially as their application grows. In order to do this, we had to kind of change the way the optimizer works. So they use a different objective function for optimization and only chose plans that were scale independent. We had to expand the language so that the static analysis was possible for a wide range of queries. We had to allow it to leverage automatic view materialization so that precomputation could make more queries possible. And we also showed how you could actually model the performance of this. So this was work that I did along with my advisors, Mike Franklin, Armando Fox, and David Patterson, as well as a bunch of grad students. All the papers are on my website if you want to learn more. And I'm happy to take more questions.
Is there a specific story you have in mind for this? You mentioned Cassandra. Was there one that you used specifically?
Yeah, so we used our own, which was called SCADS. And basically the reason, so this was a project that happened before PIQL, where basically the goal of SCADS was to have a key value store that will automatically scale up and down as the workload changes. So it has this extra component called the director, which watches the workload and uses something called model predictive control to ensure that you get consistent 99th percentile response time independent of the current workload. But really, that was kind of more for convenience. It's because I spent a lot of time engineering and architecting SCADs, so that it was very easy to bring up and bring down and bulk load for running experiments at arbitrary scale. Really, our requirements are we need a ranged partition key value store. So like hash partitioning, like I think they use in Cassandra, would not be acceptable. But if you look at something like Bigtable or HBase, that would work for us. Yeah. So we need range partitioning. We need get range. And then the more features, the better. If you give us stronger consistency, that's good because we'll leverage it. But if you don't, then you get the eventual consistency the key value store is giving you. No, not at least not based on my usage of their application.
You might not want that for ATM withdrawals.
Yeah.
Right? But there are other solutions to that.
Exactly.
So I have a couple of clarification questions.
Yeah.
Not something against. So when you use TPC-W benchmark, is it really suitable for like Twitter and the application you mentioned at the beginning?
Well, so we also did a benchmark based on Twitter itself,
Yeah,
but
so other ones so this I understand. It seems to me that this or your scalability fits this one, but do you think that your scalability fits TPC-W?
oh yeah, I mean, well, okay. So let me clarify a little bit. We only did the user-facing queries of TPC-W. We did not do the analytic queries that are in the backend. That's actually something we're still looking at. But for the OLTP type queries in TPC-W, absolutely. I mean, I think you would want slightly stronger consistency when you're actually recording orders, but there's no reason you couldn't have that. But for all of the looking up by author and kind of all of the other sorts of things they were doing, yeah, I think it fits well into our model.
My second clarification question: how do you put your work of PIQL as a whole in the map of NoSQL to database?
I like to think that it's a very nice compromise between these two worlds. So you get the performance predictability of NoSQL, but the kind of expressivity and productivity benefits of using a higher-level declarative language. I like to think of it as we took the full relational model and all of SQL and carved out the section that was scalable, leaving all of the things that could get you into trouble.
So if I compare this, for example, so things start, there is a database, people do not like database, it's not scale enough, okay, so we need NoSQL. And then with NoSQL, we couldn't express SQL queries that we like, so there's a big cardinality at home. As the scope at Microsoft here, we start to make some kind of SQL queries and some light optimization, not extensive. And then I see this work is more extensive optimization, getting some SQL from the query optimizer and doing create view maintenance. These are core things that we get them out and do them. If I put this side by side with writing queries, and there are a lot of other projects that work with transactions, elastic databases in Microsoft View have deployment logic and some other so lots of transactions and language and now humanness. Am I getting database again?
Yeah, I mean, I think I consider myself a database person. I think this is getting very close to a database. Now, honestly, I think a lot of the work that these other people are doing is very applicable to PIQL. Like all of these kind of engineering improvements that they've done.
They're all parallel to each other. I mean, just the thing. They're all parallel to each other, and they all initially built database. So do you think that in 2, 3, 4 years we are going to see the database again coming?
That's my view. I honestly think key value stores will be relegated to storage managers for higher level languages because it's just too painful to write against. And if you can get the performance benefits of using the low level gets and puts while not having to deal with that, I don't see any reason why developers wouldn't want the more flexible productive system. Yeah, but of course.
We only moved off of databases because they didn't scale.
Yes.
Right? It wasn't because people didn't like programming them and really were dying to write key value.
Yeah, absolutely, absolutely. Anything? Yeah. Sure. Oh yes.
The statistics that you needed to keep, that it did work for you, kept statistics on those indexes. A lot of times you had to groom those things, you had to take care of them. I mean, it's not like you're also keeping up to the changes in the store in order to take care of these views, make sure they're optimized.
Yep. Yeah. I mean, yeah. So I think there's probably more work to be done there. Like a big part of what people have found with these NoSQL solutions is that they're just easier to administer because they were written often by operations people and not database people. But I think you're seeing that in a lot of the new databasey products that are coming out post NoSQL stores. But I think that's kind of orthogonal to the specific problem that I'm trying to solve. But I don't see any reason why a lot of the techniques that have been appearing in NoSQL stores can't be applied to more traditional database-like things. Cool. Well, thank you very much.